This is an introductory level example that shows the application of the LRFD load combinations in the ASCE 7 standard to floor and roof loads in a typical building type structure. For this problem, let's suppose that we're examining a building that's subjected to the following loads. Suppose that we have a floor that's subjected to a dead load of 68 pounds per square foot and a live load of 75 pounds per square foot. The roof, on the other hand, is subjected to a dead load of 45 pounds per square foot, a roof live load of 20 pounds per square foot, a snow load of 30 pounds per square foot, a rain load of 15 pounds per square foot, and a wind load of 25 pounds per square foot that causes uplift. It's important to note for this example that the roof live loading is different than the live loading that's applied to the floor. And it's also important to emphasize that the wind loading on the roof acts in the opposite direction as the other loads. All of the other loads are gravity loads and act downwards. The wind load that's stipulated in this problem is an uplift force, so that means that it acts upwards. Here are the 7 load combinations that we're going to use for this example. These come from the 2016 edition of the ASCE 7 standard. Note that I've included a coefficient of 0.5 on the live load in combinations 3 and 4, which is permitted in the ASCE 7 standard when the unreduced live load does not exceed 100 pounds per square foot. Also note that combinations 2, 3, and 4 all include L sub R, S, or R. One of the first things that we'll do is modify these combinations to include a roof loading that is taken as the maximum of the roof live load, snow load, and rain load. When we make that modification, the load combinations look like this. And the next thing that we'll do is rewrite these combinations with an R in place of the roof loading. This can be a little bit confusing at first, since in one case I'm using R to represent the rain load, and then in another case to represent the roof loading. But after you work through a couple of examples, the utility of this approach should become apparent. Now we're going to consider the possibility that some of the transient and environmental loads may not be acting on the structure at any given time. This really doesn't affect the first combination, since the first combination includes only the permanent dead load. When we consider all the possible permutations of the second load combination, however, we first consider the possibility that both the live load and the roof load act at the same time as a dead load. Then we consider the possibility that only the live load acts at the same time as a dead load. Then we consider the possibility that only the roof load acts at the same time as a dead load. And finally, we consider the trivial case where neither the live load nor the roof load act at the same time as a dead load. Next, we'll apply the same idea to load combination number 3, which includes live load and wind load and roof load. Applying the same idea to load combination number 4, we end up with these 8 permutations. And when we apply it to load combination number 5, we end up with these 2 permutations. If we consider all the permutations next to each other, some of them can obviously be eliminated. For example, if we consider these 5 permutations, it's obvious to us that 1.4 times dead is going to govern over the other cases. Similarly, if we consider these permutations, it's obvious to us that 1.2 times dead plus 1.6 times the roof loading is going to govern. Further still, we could see from this that this combination of 1.2 times dead plus 1.6 times live is going to govern over the other 2 cases. And we could see that in these 2, that 1.2 times dead plus 1.6 times live plus 0.5 times roof loading is going to govern. We can go even further and show that 1.2 dead plus 1 times wind is going to govern in this case. And finally, we're left with these remaining permutations, and I've chosen this new numbering sequence rather arbitrarily. So load combination number 1 is obvious. Load combination number 2 includes 1.2 times dead plus 1.6 times live. Load combination 2R is the same as 2, but includes the roof loading, etc., etc. When we include the earthquake load combinations and account for reversible loads, we're left with the 27 permutations that are shown here. There aren't any earthquake loads in this example, however, and since there aren't any wind loads or roof loads either, we're left with the two permutations that are shown here that need to be considered. When we substitute in our values for dead load and live load into these two combinations, it's readily apparent that load combination number 2 is going to govern with a floor loading of 202 pounds per square foot. Now for the roof. Again, there are no earthquake loads in this problem, so we can eliminate these permutations. Also note that there is no live load L on the roof, only a roof live load L sub R that is included in the value of R that we defined earlier. Also note that the wind load acts in the opposite direction of the gravity loads, so we can eliminate the case where we have a positive W. And finally, since the wind load creates an uplift, using a load factor of 0.9 on the dead load will be the critical case. So that leaves only these combinations that need to be considered. Substituting in our values for dead load, roof load, and wind load, we can see that load combination number 3 gives us our maximum case of 102 pounds per square foot, and load combination number 5 gives us our minimum loading of 15.5 pounds per square foot. Even though the wind acts to cause uplift with the presence of the dead load included, even with a load factor of 0.9, we still end up with a positive or downward loading on the roof for combination number 5. It isn't always readily apparent which load combinations are going to govern and which ones can be excluded, so you always have the option of simply working out all the different permutations to find out which one results in the critical loading. That's what I've done here. I've used a spreadsheet in Microsoft Excel to evaluate all the different permutations numerically. As you can see, we end up with the same maximum roof load of 102 pounds per square foot from load combination number 3 and the minimum roof loading of 15.5 pounds per square foot from combination number 5. Using that same spreadsheet to double check my floor loadings, you can again see that we end up with a maximum floor load of 202 pounds per square foot resulting from load combination number 2. Now let's consider a slightly different version of the same problem. Let's consider the possibility that the wind load could cause either an uplift or a downforce. In this case, let's suppose that the uplift has a magnitude of 52 pounds per square foot and that the downforce has a magnitude of 38 pounds per square foot. It isn't uncommon for engineers to have to design for both an uplift and a downforce, and it's not uncommon for those wind loads to have different magnitudes in the two different directions like we're showing here. When we consider this in our load combinations, note that we have to consider both the 38 pounds per square foot downforce and the 52 pounds per square foot uplift to be positive loadings. In other words, we don't substitute a value of negative 52 into load combination number 5. Instead, we use a positive 52 and let this negative sign here indicate that in load combination number 5, the wind is acting in the opposite direction of the gravity loads. With these load combinations, we can show that with the modified loading on the roof, we end up with a maximum roof loading of 121 pounds per square foot and a minimum roof loading of negative 11.5 pounds per square foot. With the potential for a negative design roof loading, we will have to provide accommodations to keep the roof from lifting off of the rest of the structure in a wind event, or provide additional dead load in the form of ballast in order to make sure that a negative wind loading doesn't occur. And finally, we can use the spreadsheet to evaluate all the permutations of the load combinations numerically and show that the values of 121 pounds per square foot downforce and 11.5 pounds per square foot uplift are in fact the governing values for the roof loading. All right, that's it for this example. Thanks.